There's a popular and persistent saying that pumps only create flow in a fluid, and resistance to that flow is what creates the pressure in a pipe. That may be helpful in conceptualizing what's happening in a pump system, but it's not the whole story. In fact, it's almost identical to another popular but misleading belief, this one about electrical safety, that says it's not the voltage that kills you, it's the current. Well, if you know anything about Ohm's law, you know that voltage and current go hand in hand, and the same is true about the pressure and flow rate in pipe systems. This isn't rocket science, but it's not common knowledge either, even though almost everyone has used or interacted with a pump before. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about how pumps work. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that later. Let me just say right at the start that I love pumps. They're one of my favorite topics, so this is the first of 2 videos I'm doing about them. Let me know if you want to see more because there are a ton of topics we can cover. Funny enough, most engineers working with pumps aren't all that concerned with the physics of what's happening inside one. They mostly care about performance. That's because the most important job of an engineer designing a pump system is choosing the right one. That might sound silly at first. For a small aquarium pump or sump pump, you usually don't have to be very thoughtful about selection. The difference between them on such a small scale is not that significant. But, like most things in our industry, those small variances turn into large ones at scale. As pumps get bigger and their roles become more important, selecting the right one for the job becomes a critical task. For example, choosing the wrong pump to supply a city with fresh water or get rid of floodwaters can be life or death. Today we'll walk through some of the considerations engineers use to select the right pump, using demonstrations here in my garage, and even give you some tips if you ever have to choose one yourself. Most pumps used in civil engineering, and indeed most pumps you'll encounter in your everyday life, are centrifugal pumps. That means they use an impeller connected to a motor to accelerate the liquid into the discharge line. If you go searching for pumps online for smaller applications, you'll likely see them listed according to flow rate. That makes sense because it's usually what we care about. How many gallons or liters per minute can I move? But for centrifugal pumps, it's not quite that simple. Let me show you what I mean. I have a small fountain pump here rated for 2 liters per minute. If I turn it on and pump this water into a beaker, it does just about that. It takes about 30 seconds to fill 1 liter. But watch what happens if I raise or lower the vertical distance of the beaker above the pump. In fact, through the magic of video compositing, I can show you all 3 at the same time. It's very easy to see the effect the discharge pressure has on the pump's flow rate. The higher the beaker, the greater the pressure, and the greater the pressure, the lower the flow. To illustrate this further, here's a graph of my little experiment with flow rate on the x-axis and pressure on the y-axis. In this case, I'm measuring pressure as the height of a fluid column, also known as head. You can see that my experiment created a curve on this graph. In fact, all centrifugal pumps have a curve like this, called the characteristic curve. And at the risk of this just becoming a video about cool graphs, even though some might argue that it has inherent value on its own just by being a cool graph, in this case it also is a means to an end. Let me show you why it's so important. No matter what you connect a pump to, whether a single hose or a complex citywide network of water mains, it's going to have its own curve describing how much flow will occur under different pressure conditions. You can see when I change the supply pressure by adjusting this valve, the flow rate through the pipe changes accordingly. The graph of this relationship is called the system curve, and it's different for every network of pipes from the simple to the complex. A system with lots of constriction will have a more vertical curve, where no matter what the pressure is, the flow rate doesn't change much. A system with less constriction will have a flatter curve, where more pressure equals a lot more flow. A system at a much higher elevation or higher pressure will have a curve high up on the graph. System curves can even change over time. A city's freshwater distribution system will have a flatter curve during the day when more people are using their taps, and a steeper curve at night when the demand for water is lower. Stay with me because here's why this matters. If you plot a pump's characteristic curve on top of the system curve to which it's connected, you can see they intersect. This point of intersection tells you the pressure and flow rate at which the pump will operate. It's conceptually both simple and confusing. The pump doesn't decide what pressure and flow rate it will deliver. What it's connected to does. When I change my system curve by opening or closing this valve, both the pressure and flow rate created by the pump respond accordingly. So, to select the right pump for an application, you have to know how your system will respond to being supplied with a range of different pressures. Flow and pressure are important, but they're not the only considerations that go into pump selection. A pump curve sometimes also shows other important information like efficiency. Even if a pump can operate in the extreme ranges of its performance curve, it usually can't do it efficiently. Listen to the sound of this pump as I close the valve, and you can tell that it's not performing its best over the full range of flow rates. That might not matter in some applications, but if it's a big pump that requires a lot of energy, or one that will run 24/7, 365, this is something to be thoughtful about. Again, think about scale. On your fish tank pump, a little inefficiency is not a huge deal. If you're delivering water to millions of customers 24 hours a day, small inefficiencies add up quickly. And it's especially challenging if your system curve changes over time. It might seem cheaper to use a single pump that can handle a wide range of flow rates, but it's often more cost-effective to use multiple pumps so that you can always operate in the most efficient part of each one's characteristic curve. A pump curve also shows you the pressure at which it can't create any flow. Watch what happens when I raise the tube from my aquarium pump to above its maximum pressure. The liquid reaches the maximum head and stops. I have to say, despite what you'll read in nearly every internet forum about pumps, this one is not creating flow, but it is creating pressure. I'm being a little facetious here, talking only about centrifugal pumps when there's another major category that behaves a little bit differently. Positive displacement pumps trap a fixed volume of fluid and force it into the discharge line. Unlike centrifugal pumps, where the impeller can spin without actually moving any fluid, positive displacement pumps directly couple the motor to a fixed volume, no matter what the pressure is in the discharge line. As long as the motor has enough power to force that fluid out, it will happen at a constant rate. Essentially, their characteristic curve is just a flat line. I think in most cases, people who say that pumps only create flow and not pressure are specifically referring to positive displacement pumps. But if the pressure wouldn't be there without the pump, I have to contend that the pump created it. That said, I think I understand the sentiment of this idea that pumps only create flow and why it's so often repeated. It is a little bit confusing that a pump itself is not directly responsible for the flow rate and pressures under which it operates. Those properties depend on the characteristics of the system to which the pump is connected. In the case of a positive displacement pump, only the pressure is determined by the system curve. The flow rate is a fixed value. Both are still created by the pump, but only one is decided by it. For a centrifugal pump, both the flow and the pressure depend on the system curve. Given this discussion, I'd like to propose this new mantra for the internet pump enthusiast as a more correct answer to the question of whether pumps create pressure or flow. Pumps impart flow and pressure to a fluid in accordance with their characteristic curve and the corresponding system curve. Not a great catchphrase, but it is accurate. Maybe one of you can come up with something a bit more catchy. Thanks for sticking to the end of the video. If you're here, I'm guessing that means you prefer to spend your valuable free time learning new things about the world. You probably also don't enjoy watching ads like this one, which is great because Nebula doesn't have any. Nebula is a streaming service built by and for independent creators like Minute Physics, Real Engineering, Windover Productions, and a bunch of others including me. It's a way for us to try new ideas that might not work on advertiser-supported platforms like YouTube. My videos go live there the day before they publish here, with no ads or sponsorships. And we're super excited to be partnered with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and it can be tough to add another monthly subscription. That's why this bundle is such an awesome deal. For a short time, CuriosityStream is taking 26% off an annual plan. That makes it only $15 for a year of access to thousands of awesome documentaries on CuriosityStream and everything on Nebula as well. You can watch awesome long-form content on CuriosityStream, One of my favorites is The Secret Life of Lakes, which covers fascinating details of both human-made and natural lakes across the world. Or watch Tom Scott pit other YouTubers against each other in his Nebula exclusive game show, Money. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think.